Good evening. I'm Gautaman, son of Ramakrishnan from BMK section 1/1. And today I'm here to present our design and simulation project. So the Ahmed body is a simplified car model introduced by Ahmed in 1984 to study vehicle aerodynamics in a controlled way. Its shape allows researchers to analyze flow separation, wake zones, and drag forces without the complexity of a full car. According to Lienhardt and Becker in 2003, the simple geometry makes it ideal for isolating specific aerodynamics effects like the influence of rear slant angle and surface features. In this project, we use Ansys Fluent to simulate airflow around the Ahmed body. The process involves geometry setup, meshing, solving with turbulence model, and analyzing results such as pressure distribution and velocity vectors to better understand drag reduction strategies. The Ahmed body model and its schematic diagram shown here will be used as primary references for both the geometry configuration and simulation benchmarking in this study. Vehicle efficiency and sustainability goals require significant reduction in aerodynamic drag to improve overall performance. The Ahmed body serves as a fundamental benchmark in vehicle aerodynamics, widely used to study drag behavior, wake structures, and flow separation patterns. Recent research highlights that modifying the rear slant angle is one of the most effective ways to reduce drag in bluff body shapes, as shown through transient CFD simulations. This makes the Ahmed body ideal for testing rear design optimization aimed at lowering drag forces. The objective of this project is to calculate the initial drag coefficient, stimulate the baseline flow behavior around the Ahmed body with Ansys Fluent. The second objective will be to examine flow patterns and identify high drag zones, such as separation points and wake areas that contribute significantly to aerodynamic resistance. The third one will be to develop, execute, and simulate design changes to the Ahmed body that aim to lower drag coefficient. And last but not least, to assess the success of each adjustment, use post-processing findings such as velocity contours, pressure distribution, and coefficient of drag values to improve technical and teamwork abilities through joint analysis, simulation iterations, and presenting of results. Banga and Zonite in 2017 designed a curved boat tail configuration for a basic SUV based on the Coenda effect. Without using active flow control, the shape redirected airflow around the vehicle, increasing average pressure in the wake and reducing drag by 8.01%. Spoon and Guilleron in 2002 studied the Ahmed body with a 25-degree slant angle using a closed water tunnel and the electrolyte precipitation method. Their work provided deeper insight into flow separation and wake structure at moderate Reynolds numbers. And Wang in 2023 applied an optimization method to improve aerodynamic shape parameters of an aircraft by integrating a K3 turbulence model with shape optimization. They reduced the drag coefficient from 0.209 to 0.110, identifying ideal rear geometry angles that fall within validated experimental ranges.
Using the Ahmed body as a benchmark model, we design and modify the geometry in CATIA by adjusting the rear slant angle from the standard 25 degree to 20 degree. The modified model was then import into Hypermesh for pre-processing. Before meshing, we assigned boundary component by creating a wind tunnel around the Ahmed body, labeling component 1 to 5 to define each section of the model. Next, boundary conditions were applied, including the body surface, floor, inlet, outlet, and wall symmetry. As the element size of 0.095 was used, the triangle element were selected to meshing the surface. This setup ensure accuracy airflow resolution around critical aerodynamic region of the model. Using the Ahmed body as a benchmark model, we designed and modified the geometry in CATIA by adjusting the rear slant angle from the standard 25 degree to 20 degree. The modified model was then imported into Hypermesh for pre-processing. Before meshing, we assigned boundary component by creating a wind tunnel around the Ahmed body, labeling component 1 to 5 to define each section of the model. Next, boundary conditions were applied, including the body surface, floor, inlet, outlet, and wall symmetry. As the element size of 0.095 was used, the triangle element were selected to meshing the surface. This setup ensure accuracy airflow resolution around critical aerodynamic region of the model. The next step involves setting up the 3D mesh using CFT tetramesh option in Hypermesh. We begin by locating the boundary selection panel and enabling smooth boundary layer for better neo-walls resolution. In the first parameter group, the body and floor component are selected. In the second group, we involve the ribbon selection of outlet, inlet, wall, and the symmetry. And the boundary layers parameter are defined to generate the boundaries layer mesh. This setup produces 9 critical components: the benchmark model, body, floor, inlet, outlet, wall, symmetry, CFT Tantra core, and the boundary layer, all essential for capturing detailed aerodynamic behavior during simulation. After turning off all visibility button, proceed to the previous step. At this stage, the model should display as a plain brown box indicating the mesh or geometry is correctly isolated and ready for further inspection and for processing. The model setup for this project was carefully structured to ensure accurate aerodynamic analysis of the Ahmed body using CFT tool. The base geometry was created and modified in CATIA V5, where the standard Ahmed body was adjusted into 20-degree rear slant angle, a configuration known to promote significant flow separation, making it ideal for drag investigation. Once, once finalized, the geometry was input into Hypermesh for pre-processing. Using AQSolve as the CFT solver, the model was prepared for simulation and defining critical boundary condition. Pre ensure reliable and realistic flow behavior during analysis.
In Ansys Fluent, begin by selecting the Fluent option and import the mesh file generated from Hypermesh. Once import, double click on the setup module. Enable double precision to improve the numerical accuracy and set the number of solver processes to 4 for faster computation. After the model loads, you proceed to select the viscous model. For this project, we evaluate two turbulent module, which is SST-K omega, known for accurate new wall prediction, and standard K epsilon. A two-equation model commonly used for general purpose simulation. These models helps capture key aerodynamic features like flow separation and wake formation around the Ahmed body.
Assalamualaikum. My name is Muhammad Hardi. So we will proceed with the pro-processing stage. I begin by selecting the contour plots to analyze both pressure and velocity distributions. For static pressure, the values range from a minimum of negative 369 Pascal to a maximum of 121.47 Pascal, indicating a significant pressure variation across the model. The pressure coefficient, Cp, had a minimum of negative 3.07 and a maximum number of 1.01, which highlight the aerodynamic efficiency and surface pressure behavior. Moving on to velocity magnitude. The flow ranged from 0.76 to 26.22 meters per second, showing acceleration over streamlined surface. The flow ranged from. Finally, the turbulent kinetic energy varied from 0.002 to 12.39 meter per second. Identifying region with intense turbulence and energy dissipation, these data points gives a clear picture of the aerodynamic performance after the design improvement.
Next, go to the boundary condition panels and select the inlet. Set the inlet velocity to 14 meters per second. Then select the outlet and set it as a pressure outlet. Double-click on reference values, click Compute From, and select the inlet as the reference zone. Proceed to the report section and choose projected areas. A surfaces selection menu will appear by displaying the surface area values. Then double-click on report definitions, create a new report, choose force report, and set it to the measure drive. After everything is configured, go to run calculation, set the number of iteration to 1000 and start the simulation. Once complete, print out the report for drag force analysis.
Next, we test the drag result. The drag coefficient, CD, is recorded at negative 0.11717, while the drag force is approximately negative 2.835. These negative results indicates the direction of the force opposing the motion, which is expected in aerodynamic analysis. Next, the total drag force after simulation stabilized at negative 2.345. Initially, the graph shows overlapping or fluctuating lines due to the dataset not yet reaching grid independence. However, as the simulation progressed, the solution stabilized and the plot becomes more linear and consistent. This confirms that the mesh is now sufficiently refined and the results can be considered accurate and reliable for further analysis. These are results from the comparison from standard Ahmed body and the modification that we have made by reducing rear slant angle from 25 degree to 20 degree. for post-processing and comparative analysis of rear slant angle effects. In this analysis, we evaluate the aerodynamic impact of modifying the rear slant angle of the Ahmed body. The modified model with a 20-degree slant angle achieved a drag coefficient of 0.1717, which is significant reduction from the base model's CD 0.3287. This reflects a drag reduction of over 40%, indicating improved aerodynamic efficiency that are beneficial for vehicle fuel economy or aerodynamic system performance. The pressure coefficient CP range in the slant angle model is broader, with a more negative minimum CP of negative 3.074 compared to negative 1.1580 in the base model. This shows greater pressure variation, potentially enhancing flow attachment and reducing flow separation. For static pressure, the slant model shows slightly narrower pressure extremes with minimum and maximum values of negative 369.07 and 121.47 respectively. This moderation suggests a smoother pressure gradient along the surface. In terms of turbulent kinetic energy, the slant angle model exhibits lower turbulence ranging from 0.002 to 12.39. Compared to base model, higher turbulence, this means a more stable and efficient airflow over the vehicle body. In summary, the 20-degree slant angle significantly enhances aerodynamic behavior by reducing drag, moderating pressure, lowering turbulence, and supporting better real-world performance in applications like automotive design and also commercial transport.
The modified Ahmed body demonstrates a clear reduction in drag compared to the standard models. This improvement directly contributes to a higher fuel efficiency and lower carbon emissions, making it highly relevant in today's push for sustainable transportation. The aerodynamic benefits extend across multiple applications, including commercial vehicle streamlining, passenger car rear end design, and electric vehicle efficiency. Reduced drag enables smooth, more energy efficient driving, especially in heavy duty and long haul transportation. This approach is also applicable in performance vehicle aerodynamic testing, where minimizing drag and managing airflow can significantly enhance speed, stability, and energy use across a range of automotive platforms.